Hello and welcome to the second of the lectures in this week 11 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will discuss the monotonicity of an FRI, whether it is the compositional rule of inference or the BKS. We will see that they reduce to the same kind of a structure where the composition does not play a role when the input is a singleton and when we use singleton fuzzification. Let's begin by looking at some basics that are required in this discussion. Given a fuzzy set, we know what a support, height, kernel and ceiling of a fuzzy set are. Let's quickly revise them. So if we consider the set of all elements which belong to a degree greater than 0, let's denote it by SA for a given fuzzy set A. In this case, we see that it is essentially the open interval AD. The support is the closure of this SA, so that means it is the closed interval AD. Height of A is nothing but the maximum membership value attained by A. In this case, it is 1. The kernel of A is essentially the support of the height. That means when it is actually normal. So kernel of A is the set of all elements at which the fuzzy set attains the value 1. So in this case we see that it is BC. Ceiling of A is essentially the support of height, even when height is not equal to 1. So if it is normal, ceiling and kernel are same. If it is not normal, then kernel is empty and ceiling will still exist. In this case, both of them are same because it's a normal fuzzy set. What's an alpha cut of a fuzzy set? Denoted by this symbol. It is a set of all those x for which the membership value is greater than or equal to alpha. Typically it is an interval, but it could also be a union of intervals. And by the level set capital lambda, we denote the set of all distinct alpha cuts. That means alpha values in 0, 1, which lead to distinct alpha cuts of A. We call a fuzzy set convex if for every alpha cut, the alpha cut is convex subset of X. And note that, which means that X also should have some kind of a linear space structure, a vector space structure. We know what a bounded fuzzy set is. The support of A, if it is bounded, we call it bounded. Otherwise, we call it an unbounded fuzzy set. Let's revisit the ordering that we saw in the last lecture. The ordering that we are going to consider, especially with respect to monotonicity, is that of level set based ordering. What does it say? It says that two fuzzy sets are ordered with respect to this order if the corresponding alpha cuts, for every alpha cut, they are orderable in the sense of interval ordering. That means when we take two intervals, if the infimum of both the intervals, they are comparable. The infimum of the first interval is smaller than the infimum of the second interval. And similarly, the supremum of the first interval is smaller than that of the supremum of the second interval. We say that that is the interval ordering. And what we want is for if every alpha cut between these two fuzzy sets, if the corresponding alpha cuts are orderable with respect to this interval ordering, then we say that A1 is less than A2 with respect to this level set based ordering. Now, we have seen these examples before. Here we see that for every alpha cut, the corresponding alpha cuts are orderable, whereas here it is not true for every alpha cut. At least for this alpha nut, we can see that it is not orderable with respect to this given order. Now, quick recap of the covers and partitions that we have discussed. So by fuzzy covering, we mean a collection of fuzzy sets the union of whose support is actually containing X or equal to X. So essentially we want that for every X in X, there must exist a fuzzy set in this collection to whom this X belongs to non-zero membership value. A partition, on the other hand, is a covering, and there are some specific partitions. We call it a Ruspini partition if the sum of all the membership values that an X can belong to in the covering that we have considered, if it adds up to 1, we say it's a Ruspini partition. That means if you take any X with respect to that covering, the sum of membership values of this X, the different pieces of the partition, if they add up to 1, we call it the Ruspuni partition. This is one such example that we have seen. Well, we have seen many ways of classifying fuzzy if-then rules. In the last lecture, we saw one particular way of classifying it called the monotone rule basis. What's a monotone rule base? Let's consider a single input, single output rule base. If X is AI, then Y is BI, in such rules. We say this rule base is monotone if for any two rules, pick these two rules, X is AI, then Y is BJ. If X is AJ, then Y is BJ. We say this rule base is monotone whenever we pick any two rules, if you see that AI is related to AJ with respect to the level set based ordering, then we expect that the corresponding consequences are also ordered with respect to the level set based ordering. And this should happen for any pair of rules that we pick from this. Now, let's look at some examples. If we consider these three fuzzy sets as the antecedent fuzzy sets and these three fuzzy sets as the consequent fuzzy sets, it is clear that these three fuzzy sets are orderable with respect to the level set based ordering, and so are these fuzzy sets B1, B2, B3. So if we consider them as antecedents and these are the corresponding consequence, we see that we can construct a monotone rule base. So if we have A1, A2 ordered based on the indices, and if these B1, B2, B3 if are ordered based on the indices, then such a rule base is a monotone rule base. But if there is a shift in the ordering, here you see here that B1 is less than B3, when A1 is less than A2, B1 is less than B3. We see A2 is less than A3, but the corresponding consequences are B3 and B2. Clearly B3 is not less than B2, which means this rule base is not monotone. Well, we have seen that the system function of a fuzzy inference system can be seen at two different levels. One is at the classical level, which is, we can look at it as an F star, where we give an X dash, which is the input coming from the domain X. We fuzzify it to an A dash, give it to the corresponding psi tilde, which is a function from f of X to f of Y. We get a B dash, and we use a defuzzifier to obtain a Y dash. So this is a function from X to Y. So this is one way of looking at the fuzzy inference system, the system function of an FIS, when we have both the fuzzifier and the defuzzifier. Or we could also look at it as just simply psi tilde, which is a mapping from f of X to f of Y. Typically, monotonicity is discussed at the level of the function f star, the classical level, as a mapping from X to Y. Let's discuss the monotonicity of an FRI. We will see that in the case of a singleton input, when we use a singleton fuzzifier, then the composition really does not play a role. Now, there are two compositions that we have seen, the CRI and the BKS, the Bandler cohort subproduct. We see here, in this case, we are looking at using the in-phi composition, and in the case of CRI, we are looking at sup star composition. And to get the rules, we use F, which relates the antecedent to the consequence, and G to aggregate it. H and G are the fuzzifiers and defuzzifiers. Well, let's look at the case when we are given a singleton input and we are using a singleton fuzzifier. So we have some X0, which is given as the input, and we use the singleton fuzzifier. We know that it is defined like this, as an A dash, which takes the value 1 at X is equal to X0 and elsewhere it is 0. Now, it doesn't matter if you use the CRI composition, that means sup T composition, or the in-phi composition with an I satisfying NP. What we find is the B dash, the fuzzy output, is essentially R of X0, Y. This is quite easy to see. Look at this. If you have B dash of Y, this is nothing but A dash circle R at Y. In the case of sup T composition, we know that supremum over X, A dash of X. Let's use the infix notation, R of X, Y. Now, we could take this as all those X not equal to X0, A dash of X, star R of XY. max a dash at x0 star r of x0 comma y. We know that a dash of x for x not equal to x0 is 0, and this is a t-norm, which means this entire thing is 0. So what we are left with is essentially a dash of x0 star r of x0 of y. But we know that this is 1, so 1 star this is r of x0 of y. Now this is the case when we are looking at sub-T composition. Let's look at in-phi composition. So here once again b dash of y is a dash delta I r of y. Now this is given as in-for x element of x. A dash of x implies r of xy. Now once again we can split it like this: x not equal to x naught, a dash of x implies r of xy, infimum with a dash of x naught implies r of x naught. Now once again, if you see, a dash of x is 0, but 0 implies anything is 1 because it's an implication. So this entire thing is 1. So what we get is 1, and a dash of x naught is 1, and we have assumed that implication has np, which means this essentially becomes r of x naught comma y. Infimum of these two will be r of x naught comma y. So in the case we consider sub-T composition or an in-phi composition with I satisfying np, we see that the corresponding b dash is nothing but r of x naught comma y, where x naught is the input. So essentially if you look at r as the fuzzy relation, we are essentially picking that row that corresponds to x naught in the discrete case. Well, now it is clear now that b dash depends only on r and not on the composition. That is, when we are given an input and we use a singleton fuzzifier. Now we need a crisp output for this x naught. So that means we apply the defuzzification on b dash, and so the corresponding y naught for x naught is nothing but g of b dash of y, which is essentially g of r of x naught comma y. It doesn't matter what the relation r is. Well, so now this is the original form of any FRI. But now, in the case of singleton input with singleton fuzzification, and whether you use sub-T or in-phi with I satisfying np, we see that it reduces to this form where the composition does not play any role. Of course, we are fixing the fuzzifier to be a singleton fuzzifier. Now, what are the commonly employed relations that we know? If the rules are of conjunctive form, we know that we use the R-check relation. If they are of the implicative form, we use the R-cap relation. But now we want to generalize a bit. Instead of considering min for or in for I is equal to 1 to n, it's essentially min because n is finite. We could in fact generalize and consider any t norm, and let this arrow imply some implication, a general implication. They need not be related. T and this implication, they need not be related. They need not be related in the form of residuated lattice or something like that. These operations need not come from residuated lattice presently when we are discussing monotonicity. So the FRI turns out to be like this. For F, we use the implication. There is no composition here. And for G, we are using any T norm. Of course, H is the singleton fuzzifier. So we have fixed at least 3 components: the F, G, and the fuzzifier here. Of course, now the question is, what are T and I? Which pairs to consider? We want to break free from this residuated lattice structure. We want to see whether we can move out of it and go a little more general. But let's look at R implications themselves. We have a T norm T, and the corresponding R implication is given like this. What we do know is that if T is left continuous, then IT satisfies, among the many properties it satisfies at least these 2 properties. It satisfies NP, which is important because we want to remove the composition from the picture. And we know that it also satisfies ordering property. In fact, to satisfy the ordering property, border continuity is enough, but okay, let's keep left continuity for now to see this. So now, what we would like to do is consider implications which contain the set of R implications obtained from left continuous TMs. Towards this end, let's look at some classes of fuzzy implications. Let the set I denote the set of all fuzzy implications. By INP, we denote the set of all neutral fuzzy implications. Those implications are that I of 1, y is y. By IOP, we denote the set of all fuzzy implications satisfying the ordering property. By IST, let us denote the set of all strict fuzzy implications. That means what? They are strictly monotonic when x is not equal to 0 or y is equal to 1. So we know that these are the two boundaries which are fixed. They are 1, so they are a constant. So everywhere else, they are non-constant. They are strictly decreasing or strictly increasing depending on which variable we fix. Let's look at these classes in the setting of the set of all fuzzy implications to see how nicely they partition the entire set of fuzzy implications. Consider the set of all fuzzy implications, right? The set of all strict implications, of course, form a subset of it. So they form a partition with respect to its complement, the set of all non-strict implications. Now, if you consider the set of all odd implications satisfying OP, clearly it falls in the complement of set of all strict fuzzy implications. Because when it has OP, whenever x is less than y, then it is 1. When x is equal to y, also it is 1. So the entire portion above the main diagonal, they are all constant. So it is clearly not a strictly monotonic fuzzy implication. So this is contained entirely in the complement of strict fuzzy implications. However, if we consider the set of all NP implications, they overlap with all these three classes. How do we say this? Now look at the Gauguin implication. It has OP, it satisfies OP, and it has NP. So clearly it falls in the intersection of OP and NP. If you take the Kleene-Deans implication, it satisfies NP, but it does not satisfy the ordering property, maximum of 1 minus x comma y, and neither is it strict. So it is neither satisfying OP nor is it strict. However, it satisfies neutrality property. If we consider the Rescher implication, which is 1 above the main diagonal and 0 elsewhere, it satisfies OP, but it does not satisfy NP. So clearly it falls here. If we consider the Reichenbach implication, it satisfies NP, it does not satisfy OP. In fact, it is a strict fuzzy implication which satisfies NP. So clearly it falls on the intersection between NP and strict fuzzy implication. Now, are there fuzzy implications which are purely strict but does not belong to NP? Yes. Consider this implication 1 minus x plus xy square. Clearly it is strictly monotonic, both the variables. However, it does not satisfy NP because I of 1 comma y will be y square. Similarly, are there implications which are purely non-strict but does not intersect with NP or OP? Yes, look at this, max of 1 minus x comma y square. It is not strictly monotonic, it does not satisfy OP, and it is not neutral either. So this entire thing nicely partitions it. But what we want is in fact consider only implications coming from NP. So this is the class that we need to consider. Presently we will consider the case where the implications come from OP intersection IP. So we'll consider the case where the implications come from the set of all fuzzy implications satisfying both OP and NP. Now, let's look at the main result of this lecture. Let us assume that we are given a strictly monotone rule base. What do we mean by this? So we have n rules and A1, A2, A3 are orderable, in fact by their indices, and the corresponding consequences are also orderable. We'll consider a special class of fuzzy sets from which we'll pick the antecedents and consequence. So by f star of x, we'll denote the set of all fuzzy sets on x such that if A belongs there, then A is normal. That means it has a point of normality. It is convex It is continuous in the sense of the function that we understand as a function from x to 0, 1. Also, it is strictly monotone on both sides of the ceiling. So here, in fact, because it is normal, the ceiling is also the kernel, but we want that the kernel could be an interval because it's a convex fuzzy set. So either side of the ceiling, the kernel, we want this to be strictly monotonic. So we could think of a triangular membership function or a trapezoidal membership function or even any other membership function of this type. For instance, we could have triangular, trapezoidal, or we could also have the kernel. We could also have something that goes like this. Or we could have the kernel, something that falls like this. So these are some of the fuzzy sets which actually fall in this special class of fuzzy sets on X. Now, let Px and Py, which consists of the antecedents and consequence, let them come from the particular class of fuzzy sets that we have discussed now. That means they are normal, continuous, convex, and strictly monotone on either side of the kernel. This Px, which consists of these antecedents, they also form a Ruspini partition on X. This collection forms a Ruspini partition on X. Let us insist on the collection of consequence to form a Ruspini partition on Y. That happens. And the rule base that we are considering is a strictly monotonic rule base. That means the order between the antecedents is carried over to the consequence also, the corresponding consequence also. Let T be any T norm, and the implication, let it come from the class of fuzzy implications which satisfy both OP and NP. Then we can prove the system function G of the following FRI system, where we have fx, py, and this RT implication is the one where we substitute T for the aggregation and the implication coming from this class for the implication there relating the antecedent to the consequent of each of the rules, and let the defuzzifier be the LOM defuzzifier, which is the least of maxima. If that happens, we see that it is actually monotonic. The system function is monotonic as a function of x to y, as a function from x to y. Now note that the fuzzifier is not specified because we have fixed it to be the singleton fuzzifier. Well, let's go ahead and prove this result. Let's have the required part here and then we'll go ahead and prove the result. So to begin with, let's assume that we are given an x dash element of x. Now we know that the antecedents ai coming from x, they form a Ruspini partition. Now we know that these are also normal fuzzy sets because we are picking them from the special class of fuzzy sets. So we could assume that these AKs, each AK attains normality at some xk. Clearly, that means when we pick x dash is going to fall in the interval xm plus 1 for some m. For instance, so we could consider this as x1. So x, this is a2, is a1, is a2, a3, so on and so forth. So if we pick any x, it is going to fall any x dash, it is going to fall between xm and xm plus 1. So that's the first observation that we can make. For some m plus 1, we know that x dash falls there. Let us go ahead and prove in step 1 how b dash of y will look like. Note that b dash of y is equal to, this is the output. We know that this t of I is equal to 1 to n. ai of x dash implies bi of y, because we are talking about singleton defuzzification. Now this can be written as, now x dash belongs to m plus 1. It does not belong to any other interval, which means if you write it as t of I is equal to 1 to n, I not equal to m or m plus 1, a of x dash implies b of y, comma, yes, perhaps t of am of x dash implies bm of y, comma, am plus 1 of x dash implies bm plus 1 of y. Now clearly, because we are talking about singleton fuzzification and x dash does not belong to the interval other than xm plus 1. So ai of x dash is 0. When this is 0, this entire thing is 1, and t norm over entire thing is 1. So this is essentially t of am of x dash implies bm of y, comma, am plus 1 of x dash implies bm plus 1 of y. So this is our b dash of y. So notice this is what we have here. Next, what we need to find is the least of maxima. First, we claim that this b dash is normal. Hence, we go about finding the kernel. We can show the kernel is in fact the intersection of these two intervals for some values am, bm and am plus 1, bm plus 1. Let's look at what they are. We claim kernel of b dash is in fact am, bm intersection am plus 1, bm plus 1. First, let's look at this. Let's write this as Sm and this as Sm plus 1. Note that these are actually membership values of x dash in am and am plus 1. Now we know that am and am plus 1, they are coming from Px, which forms a Rospini partition. That means we know that am of x dash plus am plus 1 of x dash is equal to 1. This implies Sm plus Sm plus 1 is equal to 1. Now how would it look like? So essentially we have these two am and am plus 1. So this is xm, this is also here. Xm plus 1. So we assume that let's assume that the x that we have is here, the x dash. Now, so this is our Sm plus 1 and this is our Sm. Because note that x dash is between xm and xm plus 1. That means it falls on the decreasing part of am and increasing part of am plus 1. Now what we are doing is we are using these values essentially to modify Bm of y. Bm also, the Bi's also form a Ruspini partition. So when we do that, we take this value and this. Okay. So what we have is this. Consider this. Right. What this is will become clear presently. So now, what is kernel of B dash? Kernel of B dash is set of all y in y such that B dash of y is equal to 1. But look at it, B dash of y should be 1. Now this B dash is t of these two quantities. That means both the quantities should be 1. So this is essentially set of all y in y such that am of x dash, now we are writing it as Sm, set of all Sm implying Bm of y, this is equal to 1, all those y such that this happens, intersection y such that Sm plus 1 implying Bm plus 1 of y is equal to 1. Now note that implication, we have picked it up from this class of OP implications. That means this is equal to 1 if and only if Bm of y is greater than or equal to Sm. Intersection y such that Bm plus 1 of y is greater than or equal to Sm plus 1. So this is essentially Bm of Sm, the alpha cut of this, intersection Bm plus 1, the alpha cut with respect to Sm plus 1. So now this is what you are seeing here, essentially the alpha cuts. So let's take this as Am and this as Bm, and let's take this as Am plus 1 and this as Bm plus 1. We know that BIs are continuous and convex, so the alpha cuts will be interval. So we'll take this as Am, Bm, intersection Am plus 1, Bm plus 1. This is exactly what we wanted here. We have found this. Now, interestingly, in fact, what we can show is that this intersection is non-empty. Not only that, this intersection is in fact singleton. How do we show this? Well, we need to show kernel of B dash is in fact Bm, which is also equal to Am plus 1. Now look at this. What is Bm? Bm is essentially that element of x, element of y, such that the Bm of at Bm is actually going to take the value Sm. So Bm of Bm is equal to Sm. Now what this means is, we also know by Ruspini partition that Sm plus 1 is equal to 1. So B is also forming, because they also form a Ruspini partition, that means this is equal to Sm plus 1. Now we know that at this point Bm, if we take this figure as a reference figure, we see that Bm belongs to both capital Bm and Bm plus 1. So that means it is clear that Bm of Bm plus Bm plus 1 of Bm is equal to 1, but this is equal to Sm plus some quantity, which is essentially 1 minus Sm, which is nothing but Sm plus Sm plus 1. So that means we see that Bm plus 1 at Bm is in fact equal to Sm plus 1. But we also know Bm plus 1 at Am plus 1 is also equal to Sm plus 1. And now note that this Bm plus 1 and this value Sm plus 1, because the x dash, we have assumed that it may not exactly be the point of, it may not belong to the kernel. When it is not 1, what we know is Bm plus 1 on either side of the ceiling is strictly monotonic, either increasing or decreasing. In this case, Bm plus 1 is in fact increasing, and by the strictness, we see that this implies Bm is in fact equal to Am plus 1, which means we get the kernel of B dash. So this Bm is actually equal to Am plus 1, so this is what we get as a kernel. So now, if you are given an x dash, if you want to find the kernel, essentially the kernel in the setting that we have taken, where the antecedents and consequence, they form Rospini partitions on the corresponding x and y, and these sets are in fact normal, convex, continuous and strictly monotone both sides of the ceiling, both sides of the kernel. We see that for a given x dash, the kernel of B dash is in fact a singleton. So it does not matter whether you apply the least of maxima or the max of maxima or the mean of maxima, all of them will exactly be the same. Any such defuzzifier you apply, it will essentially be Bm itself. So from here we see G of x dash, if it is equal to LOM of x dash of B dash, is equal to LOM of kernel of B dash. This is equal to essentially singleton. So this is Bm, the value that we have got. Well, now this is what we have. Once more, what we have written here is we are taking G of x dash. We know that it is LOM of B dash. It is nothing but LOM of kernel of B dash, because we want to find the least of maxima. So we have shown that B dash actually is normal. So we are finding the kernel of B dash, but the kernel of B dash is singleton. So we have got Bm here. Well, the final step now is to show that this mapping in fact is monotonic. Okay, we will show this also. So we want to show if x dash is less than x double dash, this implies G of x dash is less than or equal to G of x double dash. Now there are two cases here. X dash may belong to xm, xm plus 1, because it has to fall in the, it is coming from x, so it has to fall in one of these intervals for some m, and it is possible that x double dash can fall on the interval which is little farther away. So let's write it as, it might be falling at xm plus p, xm plus p plus 1, or some p greater than or equal to 1. So it falls in an interval a little farther away, because x dash is strictly less than x double dash. Then clearly G of x dash is some Bm, and G of x double dash is equal to some Bm plus p. Now note that this Bm itself actually belongs to, maybe we can say Ym plus 1, and this will belong to where this is the part where Bm and Bm plus 1, they intersect, the supports intersect, and this is coming from Ym plus p, Ym plus p plus 1, and clearly this interval is in terms of ordering, so we know that Ym plus 1 is strictly less than Ym plus p. So clearly Bm is smaller than Bm plus p. So in this case there is nothing to prove, it follows quite easily. Let's look at the case when both x dash and x double dash, they fall in the same interval. This case again is quite simple, because what we have is x dash is less than x double dash. This implies if you look at this region xm plus 1, we know that am is in fact falling down. So what we have is am of x dash is greater than am of x double dash. Now if we take this as sm dash and this as sm double dash, so this is what we have. Now if we apply bm on this, because that's what we need, we see that this is less than bm of sm double dash. Now what is bm of sm dash? It is essentially the point at which, let's apply bm inverse. Now we know that bm is strictly decreasing there, so bm inverse is also strictly decreasing. So bm inverse of sm dash is essentially the bm that we are looking for, the value bm belonging to y at which bm takes the value sm dash. So this bm dash, this is bm plus 1 dash, because this is the value that bm takes sm double dash, which is essentially also falling on bm plus 1, which is what we have seen as am plus 1 dash. In fact, we should denote it by bm double dash. So we see by the decreasingness of this, this is smaller than this. So once more, this bm dash is that point at which bm takes the value sm dash, and bm double dash is that point at which bm takes the value sm double dash. We know that these are what are defining the corresponding alpha cuts, and by Ruspini, the kernel is essentially the bm dash or am plus 1 dash, and in the other case it is either bm double dash or am plus 1 double dash. And clearly we see that bm dash is smaller than bm double dash, which means this is our g of x dash, which is smaller than g of x double dash. And we see that in both the cases g is in fact monotonic. Now this shows that if you consider the antecedents and consequence in the monotone base to be normal, convex, continuous and strictly monotone on both sides of the ceiling and forming a Ruspini partition, you could use any T-norm and an implication which satisfies both NP and OP. And if you would like to use any kernel based defuzzifier, then it will be, the system function will be monotonic. Why any kernel based defuzzifier? Because the kernel turns out to be singleton kernel. Now the question comes up about illustrating them. So let's pick one particular implication, the Gauguin implication, which we know satisfies both OP and NP, and let's take a set of monotone rule bases. So allow me to present to you the corresponding system function if you use either the center of gravity defuzzifier or the LOM defuzzifier. In this case we have 4 rules. The antecedents and consequence are ordered according to the level set based ordering, and they do form a strictly monotone rule base. We see that the output of the system that we obtain, the system function, even for COG is quite monotonic. It is monotonic, and in the case of LOM it is monotonic. We see this. This is Gauguin implication, which is also an R implication, which is a G implication also. Let's look at another implication which we know is not an R implication but satisfies both OP and IP and NP. So we denote it by the MM. So it is essentially what we call the reciprocal of the Gauguin implication, but it can clearly be seen that it cannot be obtained as an R implication of some T-norm. Now for this, when we use the COG defuzzifier, we see that the system function is not monotonic. However, if you use the least of maxima, any kernel based defuzzifier, we do see that it validates our result stating that we do get monotonic system function. Now the question that comes up is, okay, we know that R implications do satisfy OP and NP, but are there other families? Yes, R implications are just one. We have seen that SN implications, there are many members of the SN implication which do satisfy both OP and NP. There are also QL implications which do satisfy OP and NP. For instance, if you consider the QL implication obtained from the product T norm, Lukasiewicz T co-norm, and the negation 1 minus x square, we obtain this fuzzy implication. Clearly, we see that this satisfies OP. For instance, the implication we have is this is minimum of 1, 1 minus x square plus xy. Now, this is equal to 1 implies 1 minus x square plus xy is greater than or equal to 1. Cancel this implies xy is greater than or equal to x squared. Since x is not assumed to be either 0 or 1, what we get is x is less than or equal to y. This is if and only, so x is less than or equal to y. So clearly this satisfies OP. Any QL implication satisfies NP, so it satisfies both OP and NP. Of course, from the family of F implications, we don't get any member who satisfies OP. And in the family of G implications, we know that the only member that satisfies OP is the Gauguin implication. Of course, these are from the basic families of fuzzy implications, but there do exist a lot more other families of fuzzy implications, like RU implications, SN type of implications obtained from uninorms and so on. And there again, you will be able to get some members which do satisfy both OP and NP. So this class of implications satisfying OP and NP, they are quite rich. They not only contain R implications, but also other implications outside of this class. Well, what we have seen is, we partition the set of all fuzzy implications into these nice classes. We knew that we had to concentrate only on the set of NP implications. And in this case, we have considered only that part where it was intersecting. We considered the intersection between OP and NP. A similar result can be proven for the case where it is both NP and strict. Note that we need NP so that we can remove the composition and concentrate only on the R. What we have seen in this lecture so far is the proof of such a result when the implication comes from the class of fuzzy implications which satisfy both OP and NP, that means the intersection of IOP and INP. But a similar result also has been proven for the case where the implication comes from the intersection of INP and IST. Well, that is the work related to showing that implications coming from the families of implications which are both strict and satisfy NP. That was a work shown by Santana and Jairam in the paper in 2016. And what we have seen in this lecture about implications coming from the class of implications satisfying both OP and NP, how the system function when you use them is monotonic. That result actually comes from a very recent work of Santhan Mandal, which was published in 2020. It should be pointed out that it was very important for us in the proof that we did have B dash to be normal. That means the kernel was not empty. This relates to a fact of what is called the coherence of fuzzy rules. That means when you consider a system of fuzzy rules and the corresponding relation, we want that for any given x dash, there exists some y such that R of x naught y is 1. This is called the coherence, and this coherence and redundancy has been quite well discussed in a paper by Dubois and others. Also, as was mentioned in the last lecture, when we consider implicative models, if to discuss the monotonicity, the rule bases were transformed into what are called at most or at least fuzzy rules. That means the antecedents and the corresponding consequence themselves were transformed, and it was that set of rule base that was considered to discuss the monotonicity. However, you would note that in the discussion that we have had during this lecture, we have not had to resort to doing any such transformations on the antecedents or the consequence. We have predominantly discussed only implication based rules, but of course there also exist works which deal with the R-check relation, where we use a T-norm to relate antecedent to consequent. So this work is contained in the first or the seminal works done by Brookhaven and Barnath in these two papers in late 2010. With this, we'll wind up the discussion of monotonicity of an FRI. In the next lecture, we will discuss the monotonicity of similarity-based reasoning schemes. Glad you could join us for this lecture. Hope to see you soon in the next lecture. Thank you again.